Welcome to the first screencast on sorting. This is the first screencast where I'm talking specifically about an algorithm and not an abstract data type. So what is sorting? Sorting is basically simply arranging data in order. So we assign an order to the data. The thing to keep thinking about throughout this screencast is, what does in order mean? For example, you could arrange things by size. We can do it by age, we can do it by their name alphabetically, we can do it all sorts of different ways, and each of those different ways implies a different order, but we can use the same sorting algorithms to produce the sorted things. Understanding and being able to implement sorting algorithms is a very important programming skill to have. You should be able to implement almost any of these sorting algorithms because it's often useful to sort things, and if the language or the particular environment you're in does not support their own sorts, it may be beneficial to be able to build your own or implement your own. And also, studying sorting algorithms provides insight into how to solve the problem. Are there different ways to address the problem? For example, can you break it down sort of recursively, or can you do it linearly? And also the analysis and comparisons of the algorithms that perform the same task. So all the sorting algorithms we're going to talk about sort things, but they have different performance, but they all do the same task. So which sorting algorithm you choose is often based upon your analysis of the situation and the complexity of the algorithm, how fast it executes. So being able to understand sorting allows you to be able to make those trade-offs when it's time to make those decisions. So Java has several built-in sorting mechanisms or methods. The arrays.sort method, there's several of them, provides methods for sorting Java arrays. They have arrays of ints, booleans, and others. The array sort uses a quick sort, which we'll talk about in the next screencast. The collections class also provides a sort method, but it's used for sorting lists. And in this case, the collections sort uses a merge sort instead of a quick sort. And both of the arrays and collections class support supplying a comparator to determine the in-orderness. So the comparator compares two objects and says this one is less than that one. So by supplying the comparator, the collections and arrays class allows you to sort the items in different orders by using different comparators. Both the merge sort and the quick sort are a big O of n log n, so they're very quick algorithms. But today we're going to talk about quadratic algorithms, sorting algorithms, and the first one is the selection sort. It's relatively easy to understand. The algorithm basically is you sort the list of items or the array by making several passes through the data. At each point, you select the smallest item at each time and place it where it belongs in the array or list. So here's a trace of how you would do it. We have the list of 5 items at the bottom. So we start with determining where the item we're going to fill. So we now say we're going to use this pos min to keep track of the minimum item in the remaining bit that we're searching through. And then we use the next to keep track of what we're considering as the minimum as we scan the rest of the array or the list. So we check to see if the item at next is less than pos min. If it is, we will reset it, but it's not. But in this case, we moved it forward. We check to see if 30 is less than 35, and it is. So we want to update where we think the minimum item is. So we update pos min, keep scanning forward, don't check, get to 20, reset. So now we've gone all the way through the things. So now we will exchange the minimum item with the one at fill. And so we have actually got the first item in the sorted array or list. So now we update fill. So now we're going to deal with position 1. Update pos min, update next, start scanning, update pause min because 30 is less than 65. Scan next forward, scan next forward, and now that next is all the way through, we can exchange pause min with fill, and we now have the first two items are correctly sorted. Update fill, update pause min, update next, check to see, and if 60 is less than pause min, and it is, so we update pause min, scan forward, check to see if 35 is less than pause min, and it is, so we update pause min, and then we exchange the item at pause min with fill, and we're done with that. So we have 3 items sorted correctly. Update fill, and this is the last time we're going to do this loop because we don't have to fill the last item because it will be the largest. Update pause min, initialize next, check to see if pause min is greater than next. It's not, so we exchange pause min with fill, which is the same place, and we're done with our outer loop, and we have our sorted array. So we don't have to check to see that last one. We've already done it, and we've got our sorted array. So what is the performance of this type of sort? The inner loop is executed n-1 times. There are n-1 exchanges, so each time we have to find the right item and put it in the right position, and once we get to n-1, the last item is in the right place. So the comparisons of checking next to pause min is done n-1 minus fill times, and that can be represented as the series n-1 plus n-2 plus 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 all the way to 1. And this series is basically known as, it can be represented as n squared over 2 minus n over 2. And so that is an n squared comparisons in the inner loop, and then you have big O of n exchanges. So this sort is a big O of n squared algorithm, and a big O of n squared algorithm is considered a quadratic sort. So it's not too bad, it's n squared, so if n gets large it gets very slow, but it's not a bad sort. The next sort we'll be talking about is the bubble sort. It's also a quadratic sort, and in this case we just compare adjacent elements and exchange them if they're out of order. So what happens is smaller values bubble to the top, the array as you'll see next, and the larger values sink to the bottom, so that's why it's called a bubble sort, because smaller values bubble to the top. So let's take this array here and pass 1, so for each we loop until the array's sorted. While it's not sorted, we'll continue looping. So for each pair of elements, if they're out of order, we swap them. So we compare pass 1, 42 and 60. We then compare 60 and 75, 75 and 83, 83 and 27, and we're going to swap them. And at this point, we finish pass 1, and 83, the largest value, is in its correct position. So we are done, and so now we don't need to search the last item. We can now do a shorter pass from 0 to 3. So now we compare 42 and 60, 60 and 75, 75 and 27, swap, and 75 is now in its right place. Continue on, 42 and 60, 27, 60 and 27, swap, and then 42 and 27, swap, and the array is now sorted. So, and we've done n-1 passes. So we have 4 passes. We know that when we've done n-1 passes and we're done with that, the array will be sorted, guaranteed to be sorted. However, sometimes the array can be sorted before we do n-1 passes, and it's easy to detect that if the array is sorted, we haven't done any exchanges of the values, and once we have no exchanges, we know that the array is sorted. So there is, if you try a bubble sort on a sorted array, you'll have no exchanges and you only need to do 1 pass. So the number of exchanges, again, is the n-1 plus n-2 series, which is n squared comparisons and n squared exchanges if you have to do all the passes. Compared to the selection sort, bubble sort is usually worse because you have more exchanges and more comparisons, unless you happen to be able to get the array sorted without doing all your passes, in which case the bubble sort will stop, whereas the selection sort will continue scanning the rest of the array. It does not have a way of stopping early like bubble sort does. And the third sort is the insertion sort, another quadratic sort. It is similar to how some card players arrange their hand. So you have your card in your hand that have been picked up, and you keep them in order. And when you pick up a new card, you insert that card in the right place of your hand. So you make room for it and slide the card into its proper place, keeping the selected cards, or the cards in your hand, sorted. So how do we do that? The trace is basically for each array element from the second to the last, will insert that item in the correct place. And what we do is we assume that we start with a subarray of one item, and we say that that array is sorted, and it is. If 30 is in the correct place in the subarray of 30. So what we do is we then take a look at the next position, and we insert the 25 into the right place of the subarray. So in this case, 25 comes first. We inserted it to the right place, and so now we have a subarray that is correctly sorted, 25 and 30. We move the next pause to the 15, and we insert the 15 into that subarray in the correct position by putting it at the beginning. And so we have the subarray 0 through 2 is correctly sorted. We move next pause forward, and we're going to insert 20 in the correct place in that subarray. So we do. We now have a correctly sorted array. Move on next pause, and then we're going to insert 28 into the correct place into our subarray. And since we've moved next pause to n-1, we have inserted all the items in the array into the right place, and we have sorted the array. So what's the analysis of insertion sort? We have to insert n-1 items. We do that n-1 times, and for each of those n-1 items, we have to consider the sorted array, where it belongs in the sorted array, sub-array. And so that's, again, a comparison of the 1 plus 2 plus 3, because you're comparing each of the sorted sub-array. So that's the number of comparisons you have to do, and then you have to do the insertion. So again, this is a big O of n squared algorithm. Again, a quadratic sort. So here's a summary of the quadratic sorts we talked about. Their number of comparisons and number of exchanges. Basically, again, they're all n squared algorithms, but they have different behaviors. Bubble sort has a best case comparisons of n. Number of exchanges of big O of 1 if it's use bubble sort on a sorted array. Worst case, they're n squared. The selection sort doesn't have as many exchanges, but you have more comparisons. So the insertion sort in general gives the best performance for most arrays, even though the insertion sort has more exchanges than the selection sort. In worst case, in general, the insertion sort is better. The bubble sort generally gives worse performance because the big O calculation does not consider the constants. So there's a lot of work overhead that we have in the bubble sort that we don't have in the other sorts. So generally, using the bubble sort's a bad idea. It's better to use the insertion sort. And finally, it's generally, you do not want to use these sorts for large n because they just have such horrible performance. N squared is a terrible growing algorithm, and you do not want to run a bubble sort over a large set of data. You want to use some of the quicker sorts that we'll discuss next time. Thank you for your attention.